The title of our next talk is quite descriptive without me giving too much of an introduction, I think. Basically, we live in a world in which algorithms make more and more decisions about our daily lives. Many people are working on improving these algorithms. Not as many are actually thinking about the implications. Say hi to your new boss. How algorithms might soon control our lives is the title of our next talk. Please give a warm welcome to Andreas Deves.
So, hello everyone. I have to say I'm really quite excited being here again. I'm a bit terrified as well, but mostly excited. And first and foremost, I want to thank to the organizers for inviting me again and for letting me speak at this really, really great conference. So, as we said before, the title of my talk is Say Hi to Your Boss, and I'm going to talk about algorithms and about like shifting decision powers from humans to machines. And in case you were asking yourself, why is this important? Well, let's just ask a friend. Here, I usually like to do that with Google Autocomplete, and normally this gives me kind of like some controversial statements, so algorithms are stupid or algorithms won't never work. But in this case, it seems like, it's pretty unambiguous that algorithms will play a very large role in this world. And as I said, this is like a big chance, because algorithms can improve our lives a lot, but it's also a problem because we're shifting a lot of the decisions that are now made by people to the hands of machines. And in many cases, we don't understand much how these machines work and how exactly they make their decisions. And so I would say my main qualification for making this talk is that I shot myself in the foot with data analysis a lot of times, and I became interested in why algorithms are doing like so many things that we don't anticipate, and why they sometimes behave in ways that seem strange and like contradictory to what we actually want to achieve with them. And so that's what I want to talk about, and we're going to do it like this. So first I will give you some theory about what an algorithm actually is, how machine learning helps algorithms to make decisions, and how this whole big data thing and like the new data-driven society age plays into this whole affair. Finally, I will show you some of the use cases for algorithms in our daily lives today. After that, we will be equipped with everything we need to know in order to start with some experiments. So I'm coming from physics, and when I try to understand something, I usually do an experiment and try to break the thing or like make it explode or whatever. And so we're trying to do the same thing here with our algorithms, and I have picked out two case studies that I'm going to present. One about discrimination through algorithms, and another one about de-anonymization. So, and finally, I want to end with some proposals and some ideas on how we can actually make the most of algorithms in this kind of setting, and also like to control and better understand what algorithms are doing. Okay, so first, as I said, I want to talk a bit about algorithms, and I just want to give you a very, very basic overview of machine learning and decision-making by algorithms. So please excuse me if there are any experts in the audience. I'm probably making like a lot of simplifications here. Okay, what is an algorithm? Here I give you an example. Basically, an algorithm is just a recipe that can be followed by a computer or a human being, and gives that human being or the computer step-by-step instructions to achieve a certain goal. So in this case, we want to activate a trapdoor, and we want to do that only if I'm on the trapdoor. So the algorithm has to decide if it's me, and then if it's me, it can open the trapdoor, otherwise it has to wait. And now this is a pretty fancy algorithm because it needs some information about me, and it needs kind of an intelligent way to decide if it's the right person that is standing on the trapdoor or not. So how does the algorithm get that information? Well, it uses machine learning. And machine learning is a way to automatically generate a model that we can check against some training data, and which we can then use to explain that data, and in addition, to also predict some unknown data. So as you might know from school, just memorizing data and like reproducing what you already know can get you through tests, but normally it won't make you pass with flying colors. So ideally, we want to have something that can, in addition of memorizing data, also make prediction about data that we have never seen before. And this is what machine learning helps us to do. In a bit more formalized way, we could like look at it as a model and some data. So here on the right, I just show you several possible models that we can choose from. Normally, we can write them as explaining some variable y as a function m for model, which takes some attributes or variables x and some parameters p, and returns some value for the quantity that we want to predict. And now we can use data to train our models and to like select the models that are compatible to our training and eliminate the ones that are not compatible to it. And you can see here on the right, we have eliminated all these models that are shown in red, whereas the models that are green can actually be compatible with our data. And now we can use those models to make a prediction about unknown data points as well, and which is shown here. And usually, you see there is some error, so some discrepancy between the model and the data that we try to explain. And this error is usually called epsilon. Now, epsilon can be decomposed further into like several parts. So there's a systematic error, which is mostly due to like miscalibrations or like measurements that we make each time when we try to like measure a given variable. So we can think about this as, for example, the speedometer in your car, which gives you intentionally a reading which is too low in order to make sure that you not overstep the speed limit. And in addition to the systematic errors, we have also some noise in our data, which is due to like either the internal process that has generated the data or the model that we use, or the measurement apparatus, that we use to capture the data. And finally, we have some hidden variable errors, which is not random noise, but which are errors that are due to variables that have an impact on the outcome of the model, but which we do not know and which we therefore cannot use to model the data. So that's the basics of like model generation. And now you probably all have heard about big data and data-driven society. And the effect that this has on model generation is threefold. For once, you can see here, for example, we have more or less the data volume in 2000 compared to the data volume in 2015. You can see that today we have a lot more data on our hands to make predictions and train models. And we also have data of a much greater variety than before. So to understand this effect, we can have a look at this graph here, which shows some random data that we measure with a pretty large noise, as you can see. And this data also contains some information. And I don't know who of you can tell me if either the green points or the red points are have a higher value. So I guess not. But now what we can do is we can just take that data and average it. And by doing that, we can reduce the amount of noise in our data. And when we have enough samples that we can look at, we can make the noise so small that we can really detect some signal in the data. In this case, the signal is just 0.01 high. And so having more data in our hands allows us to train models which can take into account smaller effects. Also, as I said, big data does not only give us more of the same data, but it gives us different kinds of data. So you can think, for example, about all the smart devices that you have in your home, like your smart fridge, your door, the maybe automated smoke detector, that all collect data about you and your interactions, and like we can use that data to incorporate it into our models and to make better predictions. And so this moves some of the noise that was in the hidden variables into the model, where we can use it to make predictions. Now, interpreting models can be hard or it can be very simple, depending on the model. So there's some machine learning algorithms, like decision tree classifiers, which are pretty easy to interpret, because we can just follow this graph here and see exactly how the algorithms makes his decision or its decision about a given data point. Other models, like for example, this neural network here on the right side, are really hard to interpret. So we can't get an intuitive feeling for how this model actually makes its decisions. And in fact, you maybe have seen those pictures here. They show basically a neural network working in reverse. So They give us an idea of how this neural network understands a picture in this case. And you can see that, for example, we have several structures here that emerge at different places in the image and that are generated by the neural network while it's recognizing the features of the image. And this method has been developed actually because it's really, really difficult to understand what a neural network is doing otherwise. So the only way we have to do that is to try to see what kind of input data the network produces when we give it a certain output data. So now what can you do with algorithms? Here I try to classify the uses of algorithms in our daily life into three different risk groups. So you could say that you have a low risk group, which basically just affects our lives on the superficially, and the algorithms that make the decisions there, if they go wrong or if they misbehave, it would be only mildly annoying. Then we have the medium risk area, where failure or misbehavior of an algorithm would be a bit more severe to our life, but wouldn't be fatal, which is only in the high risk area here, where algorithms really can take decisions that can affect human lives and that can really be life-changing in that sense. Now, a few examples for the first group would be, for example, personalization services. So whenever you go to a website like Facebook or Amazon or Netflix, the website shows you some content, and it tries to show you content which is very interesting to you. And it uses an algorithm to do that, and it tries to predict from the articles that you have viewed before, which articles, for example, you will find interesting. So this is so-called a recommendation engine, and it's in wide use in all kinds of services today. Also, we have, of course, individualized ad targeting. You might know this if you go to some website and then you view a product, and afterwards you surf around on the website, on the web, then ads for this kind of product seem to haunt you everywhere you go. And this is also due to machine learning algorithms that try to predict which kind of ads you will find interesting, and that show these ads to you on all kinds of different websites. And of course, there are algorithms that can do customer ratings. So, for example, if you want to order a product online, they could estimate how likely it is that you would pay the invoice for that article. And if it's not very high, then it would the system would only send you the article if you pay the money in advance. And of course, there are things like customer demand prediction. So the holy grail of this would be to actually know what you want to buy before you know it, and then send it to you to your door. And I think, after reading a patent, I think this is also what Amazon is trying to do in some cases. So these things just affect our lives superficially, and if something happens there, it affects us not in a very deep way. There are other uses of algorithms in our life. For example, a big topic that is coming up now with big data and more data that we can collect about individuals is personalized health. So making decisions about possible treatments and lifestyle based on data that we collect about you. For example, your heart rate, your pulse, how much you move around, how many stairs you climb each day. So this is a large potential for improving, for example, areas such as medicine, but also other ones. And we use the same or similar classification algorithms as in the applications that I showed you before. So another thing is person classification. So here we want to predict, for example, how likely it is that a person will commit a crime or will be a terrorist. And these are kind of algorithms are already in use today by, for example, governments to issue restricted travel permits and to mark some people that have a high risk profile due to the algorithm for screening. And I think there are many talks here also that deal with this problem especially. And of course, there are autonomous cars, planes and machines which are currently being developed or already in service, and which will take over driving from people in a few years or a few decades maybe. And finally, there's automated trading, which is mostly invisible to us, but which has also a huge impact because 95 or even 99% of all trades today are actually performed by algorithms and not by machines anymore. So finally, there's the high-risk area, where we have such things like military intelligence or intervention. We also have already some governments that already use algorithms to predict targets for example, drone strikes, and we also can have, of course, governments that use machine learning and algorithms for political oppression. So, for example, to train firewall systems using heuristic algorithms to detect traffic that should be filtered out. And there's also critical infrastructure services like the electricity grid or other things that are like critical to us and which are also sometimes governed or like controlled by algorithms already. So as you can see already today, we have many areas in our life where algorithms and not humans make the decisions. And if we would like plot this again on this graph, you would see that most things where algorithms decide today are actually in the green on the yellow area. And we have some things that might be touching the critical part of our lives. And now what big data and advances in machine learning will do in the coming years is probably to make, to both widen the applicability of algorithms so we can use them for domains where we couldn't use them before, like speech recognition, customer service, and many other things. And we will also like penetrate deeper into our lives, so making decisions which really can affect us on a more personal, more intimate, and more critical level. Good, so this is all I wanted to show you in theory, and now I want to use the remaining time to show you two experiments which I did. So there are lots of things that can go wrong when you use algorithms, but I picked two topics here that I find especially important. And the first topic that we are looking at is discrimination through algorithms. So here the question is, can an algorithm that is trained by a human or by an earlier manual decision process actually also discriminate against certain groups of people? You know, like discrimination still is a very big problem in our society, and we have like fought for many, many years to like push it back. And the question is, of course, now as we shift so much of the decision power from humans to machines, can we actually eliminate the discrimination that we still have in the system, or are we going to carry it over to like this automated decision making? The definition of discrimination, again here, is a treatment or consideration of a certain person that is made based on his or her group, class, or category, and is not based on his or her individual merit. So that means that we like prefer or we put at a disadvantage certain kinds of people according to their group or some protected attribute, which can be, for example, the ethnicity, the gender, or the sexual orientation of that person. And now we need a way, of course, to measure this discrimination, and the measurement that I choose here, I mean there are several, of course, has been developed in the US and is called disparate impact, and it's quite nice because it uses a very clear and simple mathematical model to explain discrimination. So basically, this model says that we have a process C, which acts on people that either have a given attribute X or don't have it. So, for example, man and woman. And we measure the outcome of this process, and we are interested in the probability of the decision being yes for a member of the group X versus the probability of being yes for the member of the other group. And so we can just have a look at the conditional probability P of making it through this process, being a member of group X equals 0, divided by the probability of making it through the process of being a member of the other group. And when we divide these two quantities, we get the parameter tau, which describes the amount of discrimination that we have in the system. And for normal purposes, we can choose a given tau, for example, 80%. And if we see that the tau is smaller, we can say, oh, this process contains discrimination. And this is nice because it measures discrimination not only if it's done intentionally, but also when it's happening inadvertently, so without wanting it. So it doesn't really matter if the process or the people in this process want to discriminate. If they do it nevertheless, maybe unconsciously, this measure can give us an idea about it. And of course, in practice, we can't deal with probabilities, so we have to measure the number of people in each category, and then we can like make an estimate of this parameter tau by just dividing this number here by these two numbers and dividing this again by this number divided by the other two numbers. So it's pretty easy, very straightforward. And now I want to show how we can use this to test a given process that we take decision power from people and give it to an algorithm. And the example that I choose here is a HR process, or a hiring process, and we want to here select candidates based on their data, for example, the CV and other data about themselves that they submit to a potential employer. And the benefits of this are, of course, saving time in the screening process and also improve the choice of candidates. And this is I choose this example because it's actually something that is widely done already. So chances are that if you have applied to a job recently, you have probably been subjected to this kind of process. And there are also several startups in the US, but also in Europe, that try to implement these kind of data-driven hiring processes. So it's something that's really already happening. Okay, again, the setup is pretty simple. We have some information about the candidate that we submit to a human reviewer, and that human reviewer makes a decision if to invite the candidate or not. And it also gives that information to an algorithm as a training data, and the algorithm tries then to replicate the decision of the human whether to hire the candidate or not. So the setup, as I say, we use the CV, any work samples, and other publicly available information about the candidate that we can get as an input. We then use a human to make the decision about a given candidate, either yes or no, and we train the algorithm on this data. So, and the approach that we have here is a so-called big data approach. So we basically try to get as much data about the candidate as we can and put it all into the algorithm and let the algorithm figure out what it does with it. So the decision model for this is rather simple. I'll show it here. In order to decide if we hire a given candidate, we can define a function S, which is the score that has several parts. One part is the score of the merit of the candidate, which is based on his or her abilities. And another part is a discrimination malus or bonus. So we can see this as increasing or decreasing the total score of the candidate based on his or her membership in a given group. And then, of course, we also have some element of luck, which we have set to 20%, for example, here. And then we just add all these three components together. And if they are larger than, so we add these two things together. And if they are larger than a given bar, we invite the candidate. If they are not, we don't invite him or her. And you can see here, the bar has a different height depending on the group of the candidate if there is discrimination in the system. Okay. Now, we can train a predictor for that model, to which we give the information Y about the candidate, and also a lot of other information which we call Z here. So everything else that we can find, for example, in public records or in other information that we can get our hands on. And then we train this predictor for to predict the outcome of the hiring process, and we can see what the results are. So since it's pretty hard to get our data to get our hands on real-world data, what I did instead here is to simulate 10,000 samples of an agent-based model where we just choose a function C and some disparate impact tau and generate training data with that. And then we can use a standard machine learning algorithm, in this case a support vector machine, to test that data and measure the discrimination that the algorithm produces. Okay, this is shown in this graph here. It's a bit complicated, so let's go through it one by one. So what we see on the x-axis is the amount of information that our algorithm has about the attribute X of the candidate. So this is the protected attribute to which we don't want to give information away. And so if we are at 0, it means that the algorithm doesn't have any information at all about the candidate. If we're at 1, it means the algorithm has all the information about the protected attribute of the candidate. And if we are at 0.5, it means that we have the correct information in about 50% of the cases. Okay, then we have our parameter tau, which is the disparate impact, and here we have set this value to 0.5. And this means that the chance of making it through the process, being a member of group X, is twice as high as for people that are not member of this group. Now, here above we see the prediction fidelity of our algorithm, which is between 86 and about 90%. and which also increases as we increase the rate gamma to which the information leaks into the system. And finally, we have here the tau, so the discrimination, the amount of discrimination done by the algorithm, measured again as a function of the information leakage gamma. Now, so what that means is that the more information we provide about this protected attribute we provide to the algorithm, the better it is able to discriminate against people in that group. So if we are here and the algorithm doesn't have any information at all about the protected group, it can't discriminate against those people. So the ratio of success between the individual groups is 1. And this is actually great because it means if we can build an algorithm that doesn't have any idea about these protected attributes, we can eliminate all the discrimination that's in the system. On the other hand, if by some accident the algorithm gets full information about these attributes, it can discriminate just as well as a human against people in either group. So that means if we give too much information to our algorithm, we will have the same problem in the hiring process as before. So we'll also have discrimination against people, not by humans this time, but by a machine in this case. And now you say probably, okay, but this is stupid. Why would we give information about this protected group to the algorithm? And of course, the answer is we don't normally. But the problem with big data and with like having a lot of different data types and different data sources on our hand is that even if we don't give that information to the algorithm explicitly, there is some amount of information about the attribute X that leaks through with all the other information that we provide. And this is basically the essence of or the dilemma of having too much data on our hands, because it's always very hard to keep information about sensitive things leaking into our data set. And of course, this is like a purely theoretic formulation now, but I actually tried to validate this by using publicly available data. So what I did was to get GitHub user data, which is which we can obtain through an API, and which gives us information about all the people on GitHub. So first, we need, of course, information about the protected attribute of the group. In this case, we choose the gender, so either man or woman. And to do that, we have to manually classify the people that we put into this study. So what I did was just to look at profile pictures on GitHub, about 5,000, and like classify the people into like man and woman. So this gave us the training data for this kind of simulation. And what I did then was to retrieve additional information about each user. So for example, the number of projects on the website, the number of stargazers, the number of followers, etc., etc. So everything I could get my hands on. And then I would use that data to make a prediction about the gender of the user just based on the information that I put into the system. So, and I want to say again, this is only a proof of concept, so I used a very small data set. I didn't do any optimization. I just wanted to see how easy it is actually to get this kind of contamination into our algorithm. So first, when I used only very basic things, like for example the number of stargazers or followers of each user, I couldn't get any prediction about the gender of the person. And I mean, this is already great, because if your colleague says, oh, you know, women, they are not good programmers, you can just now show him this data, and then you basically can disprove him. And that's because it's not possible to predict the gender from this publicly available GitHub data. But for me, it was, of course, a bit disappointing, because I wanted to prove that we can discriminate against these people, so I needed to get more data. And luckily, GitHub helps us out with that by providing a events API, which contains a full event stream of any action or almost any action that a given user has done on the site. So every time that you open a pull request, or you make a commit, or you do something else on GitHub, there's an event created for that, and you can download all the public events on the site through this website here and like process them and use them for example, data analysis. And this is what I did. So for all the users that I had in my sample, I downloaded this event data and like tried to get some more information that I could use to discriminate the gender of the people. And for example, the data that I looked at, here we see the event frequency, so averaged over all the events as a function of the hour. And you can see that now there seem to be some significant differences between man and woman in our data sets. So that's something that the algorithm could use to make a prediction about the gender. And likewise, in the type of events that we have in our data set, there are also differences in the frequency of individual event types. So that's also something that the algorithm can use to make a decision about the gender. Now, for the last thing, I went a bit crazy, and I did something that you don't normally do in spam detection. That is taking like the commit messages of individual contributors and just like inputting them into like a support vector classifier that basically looks at the frequencies of individual words in each commit and tries to find a difference in the text between man and woman. And this already gave me some good fidelity of predicting the gender, and combining it with the other information that I had, I could in fact achieve 15% better chance of like predicting the gender than by just guessing. So this is not very impressive, and we can probably do much better, but again, this was only like a proof of concept to see how easy it actually is to get this kind of information leaking into the system. And so this basically means that if we can make a predictor for the gender of the person in GitHub, the algorithm that we use to like make the decision about the hiring process can also generate this kind of information if we give it this data and use it against the people. So the takeaway from this is that the algorithm will readily learn discrimination from us if we provide them with the right training data. And also information leakage, so getting information about protected attributes in our data sets that we don't want to have there, is actually pretty easy and can happen if we are not careful. How can we fix this? Well, it's actually harder than you might think, because often we don't even have the information about the protected attributes in our data sets because we don't want to take the data from the user. I mean, imagine if you would apply for a job and your employer or potential employer would ask you for information about like your sexual preferences, your gender, your ethnicity, and plenty of other things. Probably wouldn't go down so well, but this is actually the kind of information that we would need in order to see if there is some disparate impact in our data, because if we don't have that attribute information, we cannot like calculate any fidelity or any like measure of the discrimination that is in the process. And this is what is so dangerous about this, because our algorithm can discriminate against people without us even noticing. Okay, this was already the first case study that I wanted to show, and we have seen that getting information into our data set that we shouldn't have is pretty bad. And like the worst kind of information leakage that you can imagine is if you can identify someone from the data that you have obtained for them earlier. And I mean, again, if we ask Google about its opinion on privacy, the picture is rather bleak, and it seems that many people have already gotten used to the idea that we are in a post-privacy era now. And so with the second experiment here, I want to show how easy it is actually to de-anonymize given user data even without wanting it. And what is actually de-anonymization? Well, de-anonymization means that we have some information recorded about an individual or a person, and we use that information to predict the identity of that individual in another data set. So it's kind of like your data is following you around. Even if you, like, for example, change the devices which you're working on, you change your user accounts, the system is still able to identify you just by using the data that you have like put into the system earlier, or that it was like measured of you earlier. And de-anonymization becomes an increasing risk as the data sets that we can use about individual users get bigger and bigger, actually. So the clicker, I hope it's working. Okay, now let's have a look at the math here. Though the de-anonymization is a pretty bleak subject, the math is rather fun, I assure you. So, and you maybe have played this game with some of your friends where you just think about some famous person, and your friend has to guess who that is by just asking you a series of yes or no questions. And this actually works pretty efficiently, so that after like maybe 10 or 20 questions, you can know exactly which person your friend was thinking of. And this works so well because if we have like several buckets that we can that are either true or false for a given user, we can create a unique fingerprint for a user in our system. And if you look at the probability of like having a collision, so like having two users that have exactly the same true-false values, this is getting increasingly unlikely the more buckets or the more different types of information we can put into our system. And so like the exact number or the exact probability for finding a collision between users is depending on the actual distribution of the information in the buckets. So if you have a uniform distribution, we can calculate that number. And as you can see, it decreases exponentially, which is why this game that I talked about earlier is working so well. Since, for example, if you assume that you have like 1 million famous people that you can think of, then it would probably be sufficient to have like 32 bits of information to uniquely identify them all. And we can imagine that with big data, we have many more buckets that we can actually use, so we can identify not only a few million people, but easily a few billion different people using that technique. And most real-world data sets are, of course, not uniformly distributed, so there we have more the case that many users are in the same bucket. So, for example, there are many people that like the same kind of music, so they are all like have the same information or the same attribute, and using that attribute to de-anonymize the users wouldn't do as much good, because it wouldn't help us to like narrow down the number of users in our system. But there are also many attributes that are pretty unique to each one of us. For example, the place that we are living, or the combination of that place with the work where we're going. So having a few of those quite unique data points for each user is usually already enough to de-anonymize us with a very high fidelity. And again, I wanted to see if this is actually working in practice. So what I did was to get a data set, in this case from Microsoft Research Asia, which contains GPS data of about 200 people that track their whole activity for sometimes several years, sometimes several months, and like use the data to create a movement profile, so to say. So I also have an animated version of that data. You can see here the different trajectories of individual users. I don't know if anyone recognizes the city. No, it's Beijing actually. And if you're wondering what this square here is, so I looked on Google Maps and it seems to be the university. So I guess it's like in other fields of study, whenever you need like some guinea pigs that take data for you, you go and ask students. So. Okay, so this is a pretty rich data set. We have like, in some cases, hundreds of thousands of data points per individual, and I wanted to see how easy it would be with this data set to actually de-anonymize users. So what I did was to first look at individual trajectories. So here we have like the GPS traces of the individuals color-coded, and then to apply a very simple grid, so like in this case a 4x4 grid, and just measure the frequency with which a given individual has some data in this or in this or in this square. So doing this for the 200 people gives me something like this. So this is for the 4x4 grid, and you can see the colors represent the number of times a given person has been in a given square. So white would mean that the person has been here very often. Black would mean the person has never been in this given square. And you can already see that with like the 60 examples that I show you here, many of them, they seem to be quite unique. For example, this one and this one. So it should be possible to like kind of make a fingerprint for a given user using that data. And of course, if we need more resolution to, like, for example, disambiguate users like these here, where we have like the same data, more or less, and we can't like decide which user we have, we can just increase the resolution, for example, to 8x8 or to 16x16 as shown here. And now, coming back to our buckets, if we would measure the distribution of the attributes that we have here, we can get an idea how good our choice is actually. And you can see the choice that we have made is actually pretty bad, because in the first bucket, or the bucket with the most data points, we have about like 10 to the 6, so 1 million points. But the interesting part of this curve, which is, by the way, logarithmic, is here. So in this like long tail of the distribution where we have only sometimes one or sometimes a couple of individual persons in that given bucket. So if we can get some information in these buckets, it's easy to use that to de-anonymize our users. Okay, and how do we do that? Again, we use a very simple measure. We just take the fingerprint of one user, or one trace, and multiply it with the fingerprint of another trace by pixel, which gives us then the value here on the right. And then we take these individual values here and sum them up. And this gives us kind of a score of how similar two users or two trajectories are. So doing this, we can take 75% of our data as a training set. So we just like teach our algorithm to like recognize individual users, and then we can use the remaining 25% to test how good our algorithm is at recognizing the users. Now, then we look at the average probability of identification and also of the rank that the user has in this prediction. And this is shown here. So what I show is the probability of like finding the right user within, for example, the first 2, the first 4, the first 6 users that have the highest scores for a given trace. And you can see that for even 16 squares, so the 4x4 grid that I showed you in the beginning, the identification rate is already 20% here. So we can identify uniquely 1/5 of our user by just using 16 data points. And the more data points we use, actually, the better we can identify the users in our data set. And with 1,024 individual data points, which would be quite easy to get in a real-world setting, we can uniquely identify almost 30% of the users. And again, I want to state that this is just a proof of concept, and so there has been no optimization done and no like fine-tuning of parameters or anything. And we can also use that technique to not only identify single users, but also to find similarities between users. So this could be interesting, for example, to see who is like related to whom, and who are you visiting, who are your friends maybe. And this is what I did here. So I used the same metric as before, and I just told the system to give me the users that are most similar to each other. And you can see here in green the trajectories of one user, and in red the trajectories of the other users. And the areas that are yellow are actually where the two of them coincide. You can see there are some hits here of the system which don't seem too good, but there are there's some hits also where you can see like a really big agreement between the two data sets. And I mean, I don't know who was taking this data because it's anonymized, but I would guess in this case that it's either like a taxi driver or maybe a bus driver, because you can see that we cover almost the whole Beijing area with these two traces. And so this technique makes it really, really easy to like identify users and also like find out who they are related and which other users are similar to them. And we can of course like improve the identification rate of the system by, for example, taking into account not only the spatial information, but also like the temporal information, for example, the day-night cycle, which you see here in the background. So here, the green curves have been taken at night, and the red curves have been taken during day. So like your habit of, for example, going to work in the morning and of coming back in the evening can then be used to increase the prediction fidelity for identifying a given user. And of course, we could also like change the choice of our buckets and like change the way we do the fingerprinting in order to increase the fidelity of the algorithm. So there's plenty of room for optimization. And as I said, this is only like a proof of principle, but there are other like similar works in the literature which show that with even very simple methods, you can achieve quite good identification rates in such a data set. Now, to summarize this, this means that the more data we have about a given entity or person, the more difficult it is actually to keep algorithms from directly learning and using the identity of that object for a prediction instead of an attribute. That means, as I said before, that the data which a given user or a given person generates follows him or her around the whole life. So even if you like would change all of your smartphones, all of your devices, some parts of your behavior would probably stay the same, and these could be used to identify you later in the process again with a pretty high fidelity. So that's one of the biggest risks of big data for me, because it's like very easy, if we not avoid it, to like destroy privacy of our users. Okay, yeah, thanks. So what can we do about this? I don't have all the answers, of course, but I have a few ideas, and I mean, there are lots of people working on like political and societal and technological solutions for this. So here I just want to give a brief overview of things that can be important in order to avoid these two scenarios that I have shown here. So the group of people that we probably have to educate the most urgently about this is, of course, data scientists, so the people that actually work with the data and create these algorithms. Because today, there is, in Germany, for example, you need like a 3-year apprenticeship in order to sell cheesecake. But there's nothing comparable in order to like be an algorithmicist and like to develop these kind of algorithms that have a large influence on our daily lives. So there probably should be a better curriculum in universities and even in schools, maybe to educate people not only about the possibilities of data analysis and like about scraping even like the last few % of fidelity from a given algorithm, but also about like the risks and the danger of using these kinds of technologies, especially when other people are involved. And another thing that we should be careful with is indulging data without actually needing it. So today like one of the most popular approaches in big data is just to take everything that you can get, so all the data that we can get our hands on, to give it to the algorithm and to let it decide how it uses it. And this is good normally because it increases the fidelity of our predictions, but as I explained earlier, it can be also very dangerous because maybe the algorithm can learn things which it isn't supposed to learn at all. So we should really be more careful with the data that we give into these systems. And of course, there are other things that we can do. We can try to remove discrimination and disparate impact. And there's also like a lot of academic work giving techniques and methods that we can use for doing this. But here the problem again is that most people that actually work in the fields where these algorithms are put into practice either don't know about these things or are not interested in those. So I think here we have a big potential for like improving the education of data scientists and data analysts. As citizens, we can also do something, of course. So the first thing is to not blindly trust the decisions made by algorithms. So if most people have kind of a bias to think that a decision made by a computer or by algorithm is maybe more fair than a decision made by a human. And I think this is something we have to get rid of, because algorithms, as I showed, can be just as discriminating against people as humans can. So, and if we can't question their decisions, we can at least test them and see if there's actually discrimination in the system. And now this sounds pretty easy, but it's actually very hard, because the algorithms are mostly like in the hands of big organizations or corporations, and are of course like a closely guarded trade secrets in most times. And this means that we have to use techniques such as reverse engineering in order to like find out how the internals of the algorithm might work. And I have to say I'm a bit pessimistic about this, because whereas where the companies or the organizations could use like huge buckets and huge amounts of data to train these algorithms, the amount of data that we can use for reverse engineering them is minuscule, is very small in comparison. So it's really not very likely that we will be able to make a good decision based on these kinds of techniques. And of course, we can also, one thing that we can do is to fight back with data. So by collecting data about decisions that are made about us by algorithms, and by centralizing that, we can create a lot of opportunities for other researchers and other people to analyze these data sets and to find discrimination and other things in them. And so I would encourage you to, if you are reluctant to give away your data, I can of course understand it, but in some cases, it's really the only way to make sure that someone can actually work with that data and detect also, or find injustices that are caused by it. So we have to really think about differently of giving away our data, and also creating data and machine learning against machine learning. So as a society, we can of course create better regulations for algorithms. And this is actually something that is being done. I mean, at the beginning of the year, our Minister of Justice was demanding of Facebook to open up their algorithm, and this was much ridiculed at the time, but I think it actually has some merit, because if we can't understand how corporations or companies are using algorithms, we can't know if they're discriminating against certain people or if they're treating us fairly. So having an auditing system in place that allows at least a group of people to have a look at these algorithms and to see how they're working would be a first step in the direction of making these things more transparent. And of course, making access to the data more easy in a safe way is also important to be able to detect any problems that we have with it. And finally, of course, I mean, this is maybe already too late, but we should do our best to impede like the creation of so-called data monopolies, because if one organization or one actor has all the data in its hands, we have already lost, because even if we have the same algorithms, the same technologies at our hands, most of the value in data analysis is in the amount of the data that we can have. So if there's an adversary or like an organization that has like orders of magnitude more data to work with than we, it's really unlikely that we will be able to like compete with that adversary on the same scale. So as a final word, I would say that algorithms are probably a lot like children. So they're very smart and they're really eager to learn things. And we as the data analysts or as the programmers, we have to teach them to behave in the right way, and we should try to raise them to be responsible adults. Okay, so thanks.
Thank you very much to Andreas for that enlightening talk. We do have a few minutes left for Q&A. I would like to ask you to queue up at the microphones in the Saal. If you're watching at home, we also have a human-computer interface to relay questions to us. I'd say we begin with that. Do you have a question for us?
Yes. Ruti is asking, what discrimination number would you guess for discrimination from politicians over people's choice in one or several countries?
Politicians about people's choice. You mean, can you be a bit more precise on that? I think
it's difficult to get feedbacks from the internet.
We'll get back to that question.
Okay, yeah.
We have one question in the Saal. Number 2, please.
Mm-hmm.
Thank you for your talk. Mm-hmm. Does it make any sense, or is there any hope that I am, as an individual, can fake my data patterns, or can I disturb the pattern recognition in a sensible way, in a sensitive,
yes, I think you surely can. It's only the question is only if this will be effective to, for example, protect you against de-anonymization. Because as I said, like faking 90% of your data can be useless if 10% of your data points are in buckets or like in attributes that are unique or almost unique to your person. So if you want this method to be effective, I think you would have to be really convincing. And I mean, I haven't had a look at the very big data sets, so I really can't give a quantitative answer, but I'm rather pessimistic about this approach, I have to say.
Okay. We do have a few more questions. I would ask the people in the room, if you have to change rooms right now, please do so in a quiet manner so we can do the Q&A without yelling. We do have another question in the IRC, and after that, it's number 4. IRC, please.
Atomic NGR is asking if a human is generally able to create an algorithm which is not discriminating. He's doing an analogy to random numbers where a human cannot really create truly random numbers because he or she would always have a preference.
Yeah, that's a very interesting question. I mean, it really comes down to the algorithm having the information about a protected class or not having it. So if it doesn't have the information, it can't be discriminating by definition, because it can only randomly guess if a person belongs to a given group or not. So in that sense, algorithm can be perfectly unbiased, but only if they don't have any information that gives away the protected status of an object or a person that they're making a decision about. So it's definitely possible, yeah.
Okay, the next question by number 4, please.
Thank you for your talk. You say that algorithms discriminate in the same way that humans can. But I wonder if the real challenge is that algorithms discriminate in a slightly different way than humans do. And for example, you gave the example that we can identify gender or other markers from the data set.
Yeah.
But what if these attributes that correlate with gender, class, race, etc., also correlate with other positive attributes, such as the study that you're more efficient worker when you live closer to the site of your employer. But if you have a very segregated society, that means that those who are richer are also then classified as more efficient workers and win in the scoring of potential employees. And the question is, if such a thing occurs, it's not just that discrimination can be an unintended outcome, but also if the company wants to discriminate, you cannot prove it because you say, we just hired the most qualified candidate, but in fact you just hired certain kinds of people.
Yes. I mean, that's exactly the argument about discrimination, because if you don't have the information about how many people of a given class, of a given protected status applied, for example, for a given job, you can't figure out if there is any discrimination in the process. And so that means that you have somehow to get that information into the system in order to make an audit and actually see if there's some unfair bias in there. And I mean, the other question, I don't know if I understood that correctly, is if you can like infer information about the gender from other things, and this is certainly the case because as I said in the talk, like many things, like for example the neighborhood that you live in, as you said, will give away information about protected attributes as well.
All right, we have a few more questions. I would ask you to keep them short, please. The microphone number 5 in the back.
An often heard statement is that the more data you actually collect, the less you can actually do with it, because it's just too much. Is there any scenario where this statement makes any sense?
Yeah, there definitely is. I mean, giving an algorithm more data to train with is not always a good thing. It's pretty easy to overtrain algorithms, to make a model that is like perfectly fitting the data that you give it, but that has very little predictive power for new data that you see. But in general, increasing the number of data points is always like improving the quality of the model if the data that you have is from the same model as well. So it could also happen that the data that you have is not homogeneous, so that one part of the data is fitting well with one model, but the other part of the data is fitting well with another one. So in that case, it might be difficult training a large amount of data on a single model. But it depends on the individual case, I would say. So it's really not easy to answer in that sense.
Thank you. We have time for 2 more short questions. I would ask one question from the IRC again.
Yes, in IRC, Luke is asking, isn't the black box nature of the machine learning algorithms one of the biggest problems? Can those be solved by better visualization or understanding and what it really is doing?
Yeah, for me, having algorithms that are not open to scrutiny and that we can't understand is one of the biggest problems, of course. And visualizing data can help, of course, but as I said briefly in the talk, since the space of possible parameters and the space of possible data points is so enormous, even for very small machine learning problems, that it's really difficult to produce a given visualization that would give you with a high confidence and a good information about, for example, discrimination in the data set. So it can certainly help, but I think it's not a perfect answer either.
Okay, we have time for one more question at microphone number 1, please.
Thank you. In the beginning, you displayed the arcs, green, yellow, and red, explaining that some algorithm can be more damaging. The example you made about the green was about some kind of algorithm that give to you information. Don't you think that the time of exposure influence how much is damaging? Because if I get influenced for 2 years, it's worse than just 2 days.
Can you say that again?
The time of exposure to an algorithm that influence your behavior has to be considered as a factor to understand if it's true.
Oh yeah, that's a very important point. I mean, I also had like an experiment where I look at the interaction of the algorithms with a person that he is like, for example, showing articles to, and this is like a topic of itself, I would say. So there's definitely very rich interaction that is also not captured by most models. So like the algorithm influencing the behavior of the person, and then that again influencing the actions of the person, and like influencing the machine learning of the further data. So there's definitely some feedback in the system, absolutely, yeah.
Okay, that's all the time we have. Thanks again to Andreas for the great talk.